All right, so we need some rules for dealing with probability, and that's our next section right here. What are some of these rules for dealing with probability? And one of the first things that we're going to need is some notation. And the notation that we use for probability of an event is to write P and then in parentheses E, and that's going to read as the probability of event E. You'll recall, for example, if one of our events was to draw a club, right? The probability of drawing a club, and let's say that event was probability of a club out of our deck of 52 cards, we said that was 1/4, right? The probability of whatever the event, right? So we're going to say the probability of the event is, and then whatever number is designated for that, right? And that value is between 0 and 1, right? Then we could apply this to our rules for probability, which was that the probability of any event E was between 0 and 1, inclusive to 0 and 1, right? Probability of 0 meant that it was impossible. Probability of 1 meant that it was going to be 100% uh, true. Then we talk about that probability somewhere being in between. Here, let's talk about this one. Let's say a bowl contains 12 poker chips, right? 3 red, 4 white, and 5 blue. So we've got this bowl full of poker chips. Okay, and one of these poker chips is selected at random from the bowl. So we're just going to pull one poker chip from the bowl at random. And we think to ourselves, all right, let B denote the trip vent that the chip is selected blue. So we would want to find out what is the probability that we select a blue chip. Well, we said that there were 5 chips in this bowl of poker chips out of 12. And so in proper notation, this would be our probability, 5 out of 12. Now we could give that as a decimal, right? A decimal form would be 5 divided by 12. So we take 5 divided by 12, and we're going to find that we get 0.41667, right? So rounding to the nearest 4 digits, 0.4167, right, would be our decimal right here representation of that. But all we're really talking about is the probability, and when we use our notation, this is the way that we would select that. Now, there's some special rules that deal with probability. If two events are mutually exclusive, then we can simply just add up their probabilities directly. And more generally, for any number of events that are mutually exclusive, we just simply add up their probabilities directly. Right? Another one is what we call the complementation rule. Right? The way this one works is that, well, the probability of an event happening plus the probability of an event not happening has to be a certainty, right? Because if the event happens or the event doesn't happen, you're right, right? We get a 100% probability. It's always got to happen that it's either E or not E. So we get a 100%. So the complement means that not E is the complement of E. Right? All right, so let's put this into some numbers right here. Let's say that probability of event A and probability of event B are given, and that A and B are complements, are mutually exclusive. Well, what could we say? Well, then the probability of event A or B happening is going to be the sum of those two probabilities. So we would add 0.25 and 0.40. And of course, adding those together gives us a probability of 0.65 altogether. So the probability of event A or B is 0.65. Well, how about the probability of not A? Well, to get not A, right, we're going to use that complementation rule. The probability of event not being A is going to be 1 minus the probability of A. Right? They're complements, so this must always happen. And in this case, if we take 1 and we subtract from it the probability 0.25, we're going to get our probability of not A, which is 0.75. Leaky pen, 0.75. Here we go. All right, how about the probability of it not being event A or B. Now this one seems a little bit more complex, but really this is the complement of the one above. So what we're going to do is that we're going to take 1 minus the probability of A or B. And if we figure that one out, of course, we're going to have the correct probability. So the probability here is going to be 1 minus 0.65, and that would mean that the probability of it not being A or B is 0.35. Right? All right, so not too bad, right? The basic rule, if we have mutually exclusive events, is really, really easy. We're just adding up those probabilities. Now, if the probabilities do have things in common, if they're not mutually exclusive, then what we have to do is we have to modify this rule a bit. And we say it's the probability of A plus the probability of B minus the probability that A and B occurs, right? Because if we're counting A and we're counting B, then we might end up counting the probability that A and B happening. We're counting that twice, and that's a little weird. But maybe we could show with an example here. And I'm just going to show you this one, sort of an interesting example. Let's say we have the Titan Corporation, and some of their employees have HMOs, and some of their companies have Blue Cross Blue Shield, and others have none, no health insurance at all. Not only that, some of their employees have dependent children, other people have no dependent children, right? There are 386 total employees in this corporation. So we would say, well, what's the probability that an employee chosen at random either subscribes to an HMO or has dependent children, P, H, or D? Well, here's the way that we can figure this out. We know that out of all the total events, there are 184 employees. I'll send that to the back here. There are 184 employees that have that shouldn't have happened there. There are 184 employees. It doesn't like me here today, guys. Sorry about this. Oh, well. Let's just go back up. There are 184 employees here, and we'll just use a red pen. That's easier, right? 184 employees that have an HMO, right? So we would write 184 here in red. Okay, fixing the leaky pen there, always a problem with this particular board. Okay, so we say, well, how many employees have an HMO? Well, in this case, out of 386 total employees, right, in our Venn diagram, of course, that is our total employee base, we found that 184 of them have an HMO, right? So there it is. That's our HMO right there. And of course, we found that out of the ones that the 386 employees, 253 of them, 253 right there, have dependent children. Now, some of them who have dependent children also have an HMO, and in this particular case, we see that that amount is 145 of them, right? So there's 145 of them that overlap. All right. Now, the problem would be that these are not mutually exclusive, and if we just tried to add 184 and 253, we would get more than 386. Well, that's impossible, right? So the way that we're going to figure this out is we're going to say, well, then by this rule, we're going to take the probability that we have employees that have an HMO plus the probability that they have a dependent children, and subtract away from that the probability that they have both an HMO and children. So we avoid counting them twice, right? So if we were to add these up and subtract this away, here's what would happen. Of course, we would have, get my calculator out of the way here, 184 plus 253, and then we take away, right, we would have 437 if we just added them, minus 145, and that means that we have a total of 292 employees out of 386 who have either an HMO or dependent children, right? So this overlapping rule, it kind of makes sense. We can't count this group right here twice because that would mean that we would end up with more, right? So you have to be very careful with this rule. Okay, so let's talk about one last example right here. Oil spills. This is sort of an interesting one. The U.S. Coast Guard maintains a database of the number, source, and location of oil spills in U.S. navigable and territorial waters. So we're talking about the rivers, I suppose, and lakes and canals and other places all over the U.S. The following is a distribution of oil spills, right? So the probability of oil spills, right, in the Atlantic Ocean is 0.08, right? So if we say, what is the probability that an oil spill occurs in an ocean? Well, what we really mean, of course, is that we're taking in part A right here, what is the probability that either we're in the Atlantic or the Pacific Ocean? Well, since those two actually have nothing in common with each other, we can just simply add these guys up. They are mutually exclusive, right? The probability of it being Pacific, so we would add our 0.0808, pardon me, plus our 0.037 and find that our probability was 0.045. All right, so that's for A. How about occurs in a lake or a harbor? Harbor, right? So, okay, we've got harbors down here. We've got lakes. I don't know that lakes have harbors, I suppose, but they could be something like that. But we're going to assume that harbors are kept as a separate thing from lakes. So what are we going to do in B? Well, just like we did before, we're going to add these guys up. Our probability will be 0.020 plus 0.002 plus 0.161. That's a 002 over here. Just didn't quite work out. So let's see what we're going to have. 3, 8, and 1. So our probability in this last case is in a lake or a harbor, we have a 0.183 probability of that happening. How about that it did not occur in a lake, an ocean, a river, or a canal? Wow, boy, that's a lot here. Let's see, what isn't a lake, a river, or a canal? Well, let's see, we've got ocean, lake. What lakes? Great Lakes. We got other lakes, right? We've got our Atlantic Ocean and our Pacific Ocean. We've got our rivers or canals, right? So in this last case right here, we're looking for not that. Now what we could do is that we could just go ahead and add these up. 0.008 plus 0.037 plus 0.020 and 0.002 and 0.366, right? And just add those guys up. Let's see, 8 and 10, that's 10, 17, 13, right? So bring that up, and that would be 23. So we're going to add up an extra 2 up here, 2, 2, 4, 6, 10, 13. Carry the 1 up here, 1 plus 3.433. And then, of course, our probability that it's not that is going to be probably not all of these things, is going to be 1 minus that. 1 minus 0.433. And that's going to be 0.567, right? So the probability that it's not one of those things is 0.567. What's the other way of getting it? I was about to mention that, but you know what? Maybe this might make a good exercise for you to try before you turn this in. And good luck with this week's assignment.